Multivariable calculus, we're in lesson 14.3, part 2. We left off with this example. We had just taken a first derivative with respect to x, a partial derivative with respect to x. Let's take a look at this function, 2y over y plus cosine of x, if we took this derivative with respect to y. Now, you can see what's happening right here. There's a y on top, a y down below. As we mentioned in the video at the very end, that means we need the quotient rule. And you can see I've got the quotient rule right up here. So we're going to say f of y. Well, looking at this, 2y over y plus cosine of x, as we're looking at this, here's your u, here's your v. We'll have low, which is y plus cosine of x, times d high, but again, it's the derivative of 2y with respect to y. That's just going to be a 2, minus r high, which is 2y. D low, what's the derivative of y plus cosine of x with respect to y? Well, the derivative of y is just a 1, and then the derivative of cosine of x is going to be a 0. Down below, we'll have y plus cosine of x. That's your low squared. Well, as we're cleaning this up, you can see as we distribute this 2 here, we would have a 2y plus 2 cosine of x minus, well, then we'd have a 2y over here, all over our y plus cosine of x squared. You can see our 2y's are going to cancel out. You will be left simply with a 2 cosine of x all over y plus cosine of x, whole thing squared. That would be your derivative with respect to y. Well, let's take a look right here. Find the derivative of z with respect to x, partial z with respect to x, if z is defined implicitly as a function of x and y. So in other words, z is really like a f of x comma y. So if it was written that way, of course, we would investigate this in the following way. We're going to take our derivative with respect to x down here. That's so important. That's why we pay attention to these differentials. And, the derivative of x cubed, that's simply going to be a 3x squared. What's the derivative of y cubed? Well, that's 0 because, we consider y to be a constant as we're differentiating with respect to x. But this z here, z is really a function of x and y. So this is the chain rule. We'll say 3z squared. But of course, at this point, we have to take the derivative of the inside, just like we did in BC Calc. We'll say partial derivative of z with respect to x. Now, as we're looking at this, we can see that we've got a 6xy and then a z. Z is a function of x as well, x and y. So we need to use the product rule. We'll say take your u, which is 6xy, derivative of z with respect to x, that's a partial derivative of z with respect to x, that's your u v prime. Then you need your u prime. Well, what's the derivative of 6xy? Well, that's just going to be a 6y times a z. And I hope you can see very clearly, very quickly, that we've got two partials with, partial z with respect to x. So we're going to keep these on the left-hand side. And tell you what, let's move simultaneously. And let's move this 6yz to the right. Change the sign right there. Bring this 3x squared over also. But then, with this part right here, let's just factor out a partial z with respect to x. Pardon me, I wrote another z down there. And if we did that, we'd have a 3z squared plus 6xy. And as we solve, Well, it's only going to take you a moment to see partial derivative of z with respect to x would be negative 6yz minus 3x squared all over a 3z squared plus 6xy. You might notice that each term in this problem has a factor of 3 in it, so I'm going to divide everything by 3. It's a nice way to simplify very quickly. And there you have it, your partial derivative of z with respect to x. We've done this implicitly. Well, we can also see that sometimes your function won't just be a function of 2 variables. You can have 3 variables or even more. And let's real quickly find these 3 derivatives. If we have x times sine of y plus 3z, if we wanted to find the derivative of f with respect to x, in other words, treat y and z as if these were actually constants, well, I think you can see that the only x that we have is right here. The derivative of x is just a 1, and the sine of y plus 3z is, really considered a constant in that regard. Let's go ahead and take a derivative of f with respect to y. Well, right now you can see that your y is on the inside of this trig function. So we're going to have to do the chain rule, of course. The derivative of sine, of course, is cosine. We'll have our x out in front. And then we have to take our derivative of y on the inside. The derivative of y is just a 1, so out comes a 1. So we're done. The derivative of f with respect to z, however, well, this is going to get to be just a little bit more complicated. In other words, x and y are thought to be constants. So we've got to take the derivative of this outside. The derivative of sine, like we just said, is cosine. But what's the derivative of a 3z with respect to z? Well, a 3. So a 3 is going to come out via the chain rule. So that's how we can extend and actually even take derivatives of a function of 4 variables and so forth. Well, so very often you're going to be asked to take multiple derivatives. So what you can see is pretty much this. When you have subscripts, just with x and y, the order always goes just like we read left to right. So when you see f of xx, it means first take a derivative with respect to x, then take another derivative with respect to x. X is also always going to be designated with the number 1. So you might see f of a 1 and a 1. Likewise, if you come over here, the derivative of f with that xy, it means first take a derivative with respect to x, then take another derivative immediately thereafter with respect to y. And you could see a 1 and a 2. Whereas when you look down here, this would say first take your derivative with respect to y, and then follow it with an x. However, this is very important too. Another very common style to express derivatives would be with deltas. And as you see deltas, this will go in an opposite way that we read. It will go right to left. So, as you look on the inside and out is another way to look at it. First you take a derivative with respect to x, then you'd follow it with another derivative with respect to x. Whereas you're right here where I'm circling. First you take a derivative with respect to y and then with x. So you look at that denominator, and the delta on the far right is going to designate what you do first. So that hopefully can help you out. Let's look at Clairaut's theorem. Clairaut's theorem is wonderful. It can be such a huge help. Suppose f is defined on a disk of points a comma b, As long as f of xy and f of yx are both continuous, then, oh my goodness, will this help us out? F of xy of AB would actually equal f of yx. In other words, the orders can be reversed. You're going to get the same answer. So let's go ahead and take a look at this next example right here. I think you can see with our deltas, we first are going to have to take a derivative with respect to y. And as you look at this, you're going to see, well, w is rather complicated. The derivative of xy with respect to y, that's just an x. And now we're going to need, you guessed it, once again, the quotient rule, low d high minus high d low all over low squared. Well, we'll have low, which is y squared plus 1, times the derivative of the top. E to the y with respect to y is e to the y, minus high, which is e to the y. D low is going to be a 2y. And then we'll put this all over low squared. Well, you know, it won't be too bad as you look at this to see that life is a bit complicated right now. You could most definitely still clean this up just a little bit. You could say, wow, this is x plus y squared e to the y plus e to the y minus a 2y e to the y, and you think, oh my gosh, this thing is really ugly. However, if you were to take one more derivative, remember that's what this problem's saying. Now they're saying take the derivative of this with respect to x. This whole big ugly thing is exclusively with y's in it. The derivative of that big ugly fraction with respect to x is 0, and the derivative of x is just a 1. So, wow, look at that. That works out beautifully and nicely. Well, what if, though? What if we would have used Clairaut's theorem? What if we would have said, you know what? I know it says first take the derivative of y with respect to y and then go with respect to x. What if instead we would have gone, and here's a, method 2, another way to work this out. What if we would have taken the derivative of this thing with respect to x? Well, immediately, the derivative of xy with respect to x is just a y. This other stuff just disappears. Then what? We'd say, well, now we're going to go ahead and take our derivative with respect to y, and we get a 1, and they're the same. So, using Clairaut's theorem can really help you tremendously, so keep that in mind. Let's do our last problem right here. We have a function of 3 variables, and here we don't have deltas. We actually have, the subscripts. So here we go left to right. Let's take our derivative of f with respect to x. X is inside right here, so the derivative, we need to use the chain rule. The derivative of sine is cosine, so I have the cosine of 3x plus yz. But the derivative of the inside, the derivative of this 3x with respect to x is just a 3. Let's take another derivative because now we have to go with respect to x yet again. Guys, it's the same exact thing. We're having just one x inside. So the derivative of cosine is actually going to be a negative sine. But we're going to have another derivative of 3x, which is a 3. Another 3 comes out, and we'll have a minus 9 sine of 3x plus yz. Well, now we're going to go one more derivative. This time we're going to take our derivative with respect to y. And the derivative of sine, of course, is cosine. But now, of course, as we're looking at the derivative of this yz with respect to y, we just get a z. So a z comes out. And finally, we're going to take our derivative with respect to z. And it looks like we're going to have to pick